Welcome to this Forge College Explainer. Okay, so let's just dive right into this. You know when you look at one of those massive, fully automated car factories, and you just marvel at how perfectly every single piece fits together? You've got the conveyor belts, the robotic arms, these totally pristine testing environments. Well, that is exactly what we're going to build today, but for your smart contracts. In our last lesson, we were looking at the big picture, right? We talked about overarching blockchain mechanics, specifically why Gulfstream exists to optimize the entire network's transaction pool. But today, we're zooming way in. We're transitioning from that massive macro-level network optimization straight to your local desk. We're going to build your own localized, high-speed, perfectly deterministic testing factory. And hey, no hard hats required for this one.
So think of Gulfstream kind of like an air traffic control system for the entire sky. It keeps transactions moving smoothly across the whole network, but the Foundry Suite, that's your own personal micro-level wind tunnel. It's the local testing facility right on your machine where you subject your code to rigorous, deterministic validation before it ever gets off the ground. Now, if you've been in the space a while and use JavaScript-driven runners like Hardhat, you know the drill, wiring together endless scripts and plugins, right? Well, today, we're demystifying how Foundry's Rust-backed toolchain completely shifts that paradigm. It brings everything natively into Solidity, and honestly, it makes it significantly faster and just incredibly precise. To make all of this super intuitive, we're going to treat the Foundry Suite just like a meticulously organized manufacturing plant. We'll kick things off in the blueprint room, head down to the factory floor to check out the heavy machinery, crack open our specialized toolkit, inspect the anatomy of a test on the assembly line, trace its entire execution lifecycle, and finally, we'll roll up our sleeves and fix a broken test. Let's get to it.
Section 1. The Blueprint Room, where we lay out our project and configuration.
Look, before we turn on any heavy machinery, we have to establish the fundamental rules of our factory. Foundry enforces a beautifully simple project layout where everything just has a logical place. Your actual production smart contracts, they live exclusively in the SRC folder. Your unit and integration tests are totally isolated over in the test folder, and external dependencies or libraries neatly sit in the lib folder. But the real star of the show here in the blueprint room is a file called foundry.toml. This is your master configuration. It dictates your compiler versions, optimization rules, and even your default network connections. And because Foundry insists on the standard layout, it automatically discovers your tests without you having to write any of those tedious path wiring scripts. It just works. Section 2. The heavy machinery. Let's look at the Foundry CLI tools. All right, blueprints are organized, so let's hit the factory floor. This is where Foundry's Rust-backed toolchain literally makes traditional JavaScript runners look like they're stuck in slow motion. We already met foundry.toml, the brains of the operation. Next up is Forge. This is your tireless, lightning-fast assembler. When you type commands, Forge is the engine compiling your code, managing incremental caching so you're never pointlessly recompiling, and generating your test reports. Then we have Anvil. Think of Anvil as your temporary, localized sandbox. It spins up an ephemeral local node, giving you a completely safe, blank slate blockchain to play on. And finally, forge-std. This is your precision toolkit. It's packed with helper functions and assertions that make writing tests in Solidity an absolute breeze.
Section 3. The Specialized Toolkit, diving into forge-std and cheatcodes.
Now, if you want absolute mastery over your development pipeline, you have to understand cheat codes. These things are essentially a reality-bending remote control for your testing environment. Think about it. In the real world, you can't just fast-forward time or magically rewrite someone's bank balance, right? But inside your Foundry factory, using the VM namespace, you literally have godlike powers over the Ethereum virtual machine state. Need to see what happens if a contract is time-locked for 30 days? Bam, just use a cheat code to warp time forward. Need to pretend you're a specific user holding exactly 100 Ether? Cheat codes let you impersonate them and alter their balance instantly. This crazy level of deterministic control is exactly what makes Foundry so powerful.
Section 4. Anatomy of a test. How we actually write these Solidity tests.
Okay, let's grab an actual piece of material moving through our factory, the test contract itself. Every good scientific experiment needs a completely pristine, uncontaminated workspace, right? Well, in Foundry, we get that by using the setup function. It's a brilliant, completely Solidity native convention. Basically, before every single test runs, setup executes. It's totally gas-free within this testing context, and its only job is to deploy a fresh, isolated state. In this quick example, it's just creating a brand new counter contract. What this does is guarantee that test A won't accidentally leak data or state into test B. It gives you absolute 100% isolation.
So once that pristine setup is ready, how does Forge actually know what to test? It's almost too simple. Foundry's auto-discovery just sweeps through your test files and looks for any function prefixed with the word test, like test initial value or test increment. When it finds one, it executes it right inside that newly forged ephemeral EVM instance we just talked about. There are no massive, complex testing libraries to import and absolutely no context switching between JavaScript and Solidity. You're writing your tests in the exact same language you use to write your smart contracts.
Section 5. The test execution lifecycle, or how this automated pipeline actually runs.
So how exactly does this whole automated assembly line sequence play out when you sit at your terminal and type forge test? The runner actually follows a very strict, deterministic 5-step pipeline. First, it compiles your code and smartly caches it. Second, it deploys your test contracts directly into that local Anvil sandbox. Third, it runs that setup function to totally isolate the state. Fourth, it executes your specific test logic. And finally, and this is the absolute key to its crazy speed, it takes a snapshot of the state and restores it, essentially resetting the sandbox for the very next experiment. It does this over and over again, thousands of times a second, which gives you blistering fast feedback.
Now, here's a question that always pops up in our more advanced programs at Forge College. What happens if your contract needs to interact with a massive DeFi protocol, like Uniswap? You obviously can't mock all of that locally. Well, because the Foundry pipeline is so perfectly deterministic, you can just command Anvil to create a fork of a live mainnet node. It effectively downloads the current state of Ethereum directly to your laptop. So you can validate these really complex integrations against real-world data without changing a single line of your underlying test code. You literally just tweak a configuration in the blueprint room and you're good to go.
Section 6. Fixing a broken test. Time to use our traces and cheats.
Even the best factories experience a malfunction every now and then. So let's walk through fixing a broken process. Imagine we've written a simple bank contract, but oops, the withdraw function accidentally forgets to verify if the user actually has enough money before handing over the cash. In Web3, we call that a career-ending catastrophe. So, to test this safely, we write a test using our toolkit, specifically the vm.expectRevert cheat code. This cheat code basically tells the system, hey, I expect the very next line of code to crash and burn. But because our buggy bank doesn't check the balance, it actually sends the money. The test fails. By running the command forge test with the verbose flag, Foundry spits out a beautifully detailed, low-level EVM trace that shows us exactly where the assertion mismatched.
Reading that trace is literally like looking at an X-ray of your code. It lets us apply the perfect fix right at the source. We just jump back over to our simple bank contract and add a super simple, elegant require statement. We just require that the sender's balance is greater than or equal to the amount they're trying to withdraw. Now when we run the test again, the contract behaves safely. It correctly reverts the transaction. Our vm.expectRevert cheat code catches that revert, and our failing test instantly turns a very satisfying green.
Section 7. Conclusion. Let's look at our key takeaways.
As we wrap up this factory tour today, let's just reflect on why this is such a massive leap forward. By tossing out clunky external JavaScript scripting and replacing it with concise Solidity native patterns, Foundry prioritizes two massive things: blistering speed and absolute deterministic control. You completely eliminate the mental fatigue of context switching between languages. And honestly, whether you're testing tiny local units or massive forked integrations, you have complete, granular authority over every single aspect of your testing environment. You aren't just a coder anymore. You are the manager of a highly tuned, state-of-the-art testing factory.
To explore more advanced Web3 topics and to really dive deeper into the courses and community programs we offer, make sure you visit forge.college. It is absolutely the best place to elevate your understanding of these frameworks.
But hey, before you go, I want to leave you with a bit of a provocation for our next explainer. Now that you understand the individual pieces of this factory, how are you going to map these exact tools into concrete continuous integration scripts? How will you handle fork pinning strategies as your pipeline inevitably scales up? We're going to tackle that exact challenge in the next lesson. So until then, I'll leave you to ponder this. Exactly how robust and unbreakable can your development pipeline really become when you have total deterministic mastery over the machinery?
Thanks for watching, and I'll catch you in the next one.